40.
Before the okay. Number 40. Yes, we accept. Accept. Okay. So the recorder has 5 minutes to prepare. Please write the name on the blackboard. Reviewer, who will be reviewing? Okay, reporter, take the floor.
Hello everyone, I am a reporter from Team Relativity. My name is Ta Xiaolo. I'm going to talk about problem number 14, the ruler trick. So here's the problem statement. If you place a ruler on the edge of a table, throw a ball at its free end, the ruler will fall. But if you cover a ruler with a piece of paper and repeat the throw, then the ball will bounce off. And I have to explain this phenomenon and investigate the relevant parameters. So the phenomenon looks like this. And here's our main focus. So why does this phenomenon happen? And I have to experiment the relevant parameters. So here's the outline of my report. So in my theory, I'm going to talk about the lever system with the torque and the aerodynamic about this problem. And I'm going to use Flow 3D for my simulation. And then in my experiment, I'm going to change the placements, the material, and length. And here's the first observation. So here's the effect of paper. So for the test results, we can know that covering the ruler with a piece of paper can prevent it from falling off. So here, this one fell off, and that one didn't. And then here's the next observation. So I fold the paper up or lay it flat, and from the observation, we know that the paper needs to be flat for this phenomenon to happen. And then my next observation is drop ball or place ball. And as you can see, if I drop the ball, it won't fall, but if I place it on the ruler, it will fall. And my final observation is about how the airflow generates. So I put some flour on the edge of the table and cover it with a piece of paper and repeat the throw. And the flour got behind the table, right here. And then because that means there's some airflow going into a paper, so that's going to be what I'm going to talk about. So in my theory, I'm going to separate this into a lever part and an aerodynamic part. So the lever part is when the ball made contact with the ruler, it will flip due to lever principle. And we could go deeper and calculate the clockwise torques and the counterclockwise torques. So if the clockwise torque is the torque ball, the torque right of the ruler, and then the counterclockwise torque is torque left of the ruler and the torque paper. And if the torque ball plus its torque right is bigger, it will flip. But if the torque left and torque paper is bigger, there will be a support from the table. And then I'm going to talk about the support coefficient of my ruler. So the ruler might have some bending and recoil in this phenomenon. So we could use this equation to find out the alpha, which is how this ruler would support if the force is hit onto it. And then these are different materials have different alpha. And then I use force sensor here to know the vertical force I put on this ruler, and this delta is this change in this length, in this like. And then, so if we consider support coefficient alpha into the equation, it will look like this, and then we could get the torque ball expression as this. And then we're going to consider the ball velocity and initial height, and then we're going to assume these parameters as these. So if we combine all the equations, we could get an L expression as this. And then we put this equation into Python and set these parameters, and then I could get a color plot of how this equation means. So the color here means the ruler length. The darker the color is, the ruler is shorter, and the lighter the color is, it's longer. So as you can see, if I drop it from a very high height and contact it very fast, it will need to be a very long ruler to hold everything up. But if it's like dropped in a very small place, the ruler only needs to be very small to hold up. So on the lever's viewpoint, we could simply put it as if the ruler is hit harder, it will be easier to flip. And the torque I just talked about will apply on vacuum circumstances. But there's aerodynamic behind this phenomenon. So because the observation I did, there's airflow flowing inside this system. So we're going to simulate the airflow and show what's the phenomenon like. So I'm going to use Flow 3D to simulate some of the aerodynamics. And then here's a brief process of my simulation. So here's a 3D layout of the thing I created, and then I'm gonna simulate from the initial condition to the final condition, which the ruler touches up. And then in the simulation, it uses Navier-Stokes equation to do the computational fluid dynamics. And then, so here's the simulation. So the color here means the pressure, air pressure. And then I set different omegas for the rulers, which is the angular velocity, and here's a fast, middle, and slow. And these videos are slowed by 125 times in real life. And then if we look at the final frame, we can know that these are the different pressure difference. And the pressure difference will always form. But in faster movement, there will be a bigger pressure difference. And if pressure difference bigger, the air pressure onto the paper will be bigger. So that means if there's a harder hit on the ruler, it will be a bigger air resistance, like an air pressure resistance. So, and then I'm going to compare the different places onto the ruler, like P1, P2, P3, and P4. and then this is the waveform looks like. So it will oscillate. Here's the pressure. Here's the time to pressure chart, and then at first it will oscillate because the air cavity resonance. So if you push the air, it will not move uniformly because it has some viscosity, and then it will have something with the other side of air. And then, but the important thing we're looking for is the air pressure drop at the behind. So we compare every the fast, mid, slow here means the ruler's angular velocity. So we can know that the faster the ruler's angular velocity, it will form a pressure difference, very big and very fast. And while the slow one is not forming a big pressure difference and it's very slow. It looks like this. So here's the theory of air pressure. So the pressure difference will form in the air pocket when it's in contact, and the air pressure is due to the air pressure difference, the pocket size, and how much open airflow. So I use a platform full of holes and do the observation. It will flip easily because when the pressure difference forms, a lot of air could refill from the bottom holes, so it will not have a big pressure difference in that way. So here's my assumption, my theory. So if I put here, the blue one is the clockwise torque, and the green is the counterclockwise torque. If the drop height equals 0, I will put it on there, it will fall. The reason for that is the ball is heavier than the paper. But if the drop height is between the flip point and 0, it will bounce off like that because there will be air, it will form an air pocket and there will be air pressure. But if it's a lot bigger than if the drop height is bigger than the flip point, it will just flip. The air pressure couldn't hold it up also. So and because the air inside isn't uniform, as you can see, a lot of different ways it will. So it's very hard to find a closed form equation for this phenomenon. So we could do the experiment to know some of it. So here's the experiment. I think the parameters are the weight of layers, weight of papers, the length of ruler, the support coefficient for the ruler placement, and the paper placement. So here I use tracker to track the ball's velocity and use slow motion camera to measure the contact time. And I'm going to find the torque ball flip point in every experiment. And I'm going to change the ruler or paper as my relevant parameters. And I'm going to use Python to answer my results. So the theory lines, orange is from the torque theory, and the blue dots are the experimental results. And here I'll set up, I use different things. And I made a ball dropper so that I could make sure my drop are the very same time and we will not change from experiment to experiment. So here's the first experiment about different layers of paper. So I used 1 layer, 2 layers, 3 layers, and of A4 papers, all the way to 5 layers, and I set the parameters on the right like that. And here are the results. So here's the weight of paper is grams to highest flip point torque. And then we can see that the difference between the theory and the experiment is the air pressure affecting it. And then the heavier the paper, the more torque it can hold. And then the reason, as you can see, the air pressure gets little and little as the weight of paper increases, because when there's more weight on the paper, it will be harder for it to form an air pocket. So as you can see, this is a very big air pocket, while this one has barely any air pocket. So air pressure gets less significant because it's hard to form air pressure in this situation. And then change the different length of ruler with 30 to 10. And then this is the length of ruler to highest torque graph. And then we can know that longer the ruler, the more torque it can hold. So the difference is still the air pressure affecting it. And then this part, it has a more air pressure than each other because it's a 20 centimeter ruler. The reason for that is because if the ruler is too long, it will be easy to flip everything. But if it's too short, it will form only a little air pocket. So the mid size, 20 centimeters is the best. And then my next experiment is about the ruler placement. So I just pull it out every time do the experiment, and different length covered. So the results are like these, and this is the length of covered ruler to the highest torque chart. And then as you can see, here's still the air pressure, and more covered ruler, the more torque it can hold. And here's the 20 centimeters covered has the highest air pressure, and the reason for that is same as the last one, because it's not too long or not too short. And then my next experience about the type of ruler have different support coefficients. So here's the support coefficient of ruler to the highest torque. And then we can note that bigger support coefficient, the more torque it can hold, and here's the air pressure. And then my final experiment is about the paper placement. So I place paper in different orientations and then see what's going to happen. And for different orientations, you have a very big difference in this flip point. So it will affect the result by a lot. The reason for that is if the air pocket has a big opening to the outside. Like this one, it only has a very small opening, so the air pressure difference could be formed in a very very strong, and these ones are the air could refill very fast, so it will not hold it and it will just fall off. So the shape of air pocket would decide if the air pressure difference will form easily or not. So here's the conclusion, and the problem statement is I have to explain this phenomenon, investigate parameters, and covering a paper would prevent it from falling off. And in my theory, the lever part, I talk about the torque ball expression, and then it will flip on easier hit. And then my next theory is aerodynamic, and we can see from this chart the time to pressure difference. And then if the ruler is going up very fast, it will form a big pressure difference in a short time, while the slow one does not. So in the aerodynamic part, it's the bigger hit, the bigger air pressure difference. So here's a basic assumption, which is just if I put it on it, it will flip because in a torque, the ball is just heavier than the paper. And if it's between the drop height and flip point, if it's between 0 and the flip point, it will just bounce off. But if it's too big, it will not. The big air pressure will not hold it up also. And so here's my conclusion on all my experiments. So here are the parameters that will increase the air pressure. So if I have a thin layer of paper, that will form it very easily, and the 20 centimeters ruler, and higher support coefficient ruler, and the paper and ruler needs to place parallel. And these are the parameters that prevents the flip. So if I have the thick layers of paper, because if I have thick layers of paper, it will be heavier, even though it's harder to form air pocket, but the heavier paper is more significant in this phenomenon. And if you use a longer ruler and higher support coefficient, and then the ruler and paper needs to place parallel. And that's my end of my presentation. Thank you.
Okay, question from opponent.
So the first question I would like to ask the reporter is, does the reporter agree that the material, the ball, ruler, or paper affects the result of the experiment?
Yes.
Okay, so then how do you define the fall of the ruler?
When the fall of the ruler means if it takes the paper and the paper needs to flip also. Because sometimes when I do it,
So you fit all the way to the ground?
yes, because sometimes the ruler just slips, and I don't consider that as flipping the whole thing.
Okay, I understand. And then do you have the answer of what will happen if the ball is extremely flexible?
The ball's
Extremely flexible.
yes, but it will just depend on how the impulse and how much time contact with the ruler.
Okay, so do you consider the friction of the platform that you place the ruler and the paper on? So because I think you use different platforms in your experiment. So do you consider the friction?
No, but it will have a very little effect on the experiment.
Okay, and so that's all for the question. Thank you.
Okay. Opponent has 3 minutes to prepare. opponent take the floor.
So, honorable judges and fellow competitors, this is Team Trivial, and I'm going to report problem 14, ruler trick. So, the problem statement is the above, and we think the key points are the causes of ruler remaining on the table, and the motion of a ball, and the edge cases, for example, the extreme elastic ball or ruler. So, for the reporter's theory, the reporter used Flow's 3D numerical simulation and to simulate the pressure difference. And then they use aerodynamics to support the coefficient of the ruler elasticity and lever discussion. And then they calculated the torque and made color plot for easy discussion. And then for the experiment, the reporter said they analyzes the ball and bounce of the ball, and they use flour to visualize the airflow, and it proves the qualitative theory. And then they compared experiment with table of holes, which proves the qualitative theory also. And they notices the difference due to air pressure. Okay, so for the conclusion, the reporter says the parameters that affects the result of the experiment is the weight of the paper, the drop height, the ruler length, and the paper orientation. And so the theory and the experiment agrees quantitatively. Yeah. And so here are some remarks to the reporter. So those 3D simulation to simulate real scenario is very good, and the discussion of edge cases of the critical drop height is also explained clearly. And for the quantitative equation, it is explained clearly also. And the reporter also discussed plenty of parameters. And for the suggestions, the reporter did not consider the friction effects on the result of the experiment. So, and they didn't discuss the extreme cases of paper stiffness or the ruler or the ball's elasticity. And they lack the theoretical model for paper placement. So now I would like to invite the reporter.
Okay, discussion.
Oh, wait, so for the theory, we would like to discuss the edge cases, which is extremely elastic ruler or extremely elastic ball or extremely stiff or soft paper. And then we would like to discuss paper orientation or paper shape, deformation, or the ruler shape or deformation effects on the experiment. And for the experiment, we would like to discuss the definition of the ruler's fall and the friction of the platform and how to fix the theory with the friction. And the last thing we want to discuss with the experiment is the fixing of the ball drop height and the ball drop position. So now I'm going to invite the reporter.
Okay, reporter.
So I would like to ask you with the friction first. So you said friction affects really small on the result of the experiment, right?
Yes.
So can you prove this?
Yes. Can I use the?
Yes, yes.
So when it flips, here's the table, and then it flips. It's based on the middle point here. So the friction isn't really an important factor here in this phenomenon. Do you think it will affect a lot?
Yes, can I use this? Okay, so if first you place the paper on the platform, right?
Yes.
So when the ruler here moves up, when the ball hits the ruler, so there will be two forces over here that the platform acts on the paper. So over here and over here, right? So this clearly affects the result.
No, because in my model, I only have this contact point when it's got hit by a ball. So it's only this part is as the middle part, and for me, this isn't a consideration because for my model, flipping, if it needs to be everything flips, it will count as flipping, and it will not have a double force.
So you think the friction of the platform is negligible, right?
Yes.
So you simplified this part to fit your theory.
Yes.
Okay. So now I'm going to discuss with you with the edge cases. So first, can you tell me what will happen if the ball is extremely elastic or extremely extremely close to a rigid body?
Look, in my theory, I have in my torque ball expression, I consider contact time. So elasticity will change its contact with the ruler, right? If it's very elastic, it will just, and it's not, it will just take a long time. So it will be considered into my.
Force that the ball acts on the ruler will be small, right? Because the collision time is long.
It depends. Sometimes it will separate.
Separate?
If,
What do you mean separate?
if its contact time is longer, sometimes it will separate due to the ball's texture.
Okay, so how about if the ball is extremely close to a rigid body, what will happen?
Can you explain it more?
So if the ball is really hard, and what will happen if it hits the ruler?
It really just depends on the contact time because it would yeah, its mass is right there and it would depend on if it's contact long or contact short.
So when the contact's long, what will happen?
It will be easier to fall.
Okay, when the contact. Okay, so you agree that if the ball is extremely close to a rigid body, the contact time will be very short, right?
Yes.
And when the ball is extremely elastic, the ball will be the contact time will be very long, right? Okay, so can you say again what will happen if the ball is extremely elastic? Is it less likely to fall or more likely to fall?
It depends on its contact time.
So when the contact time is long, it is.
If its contact time is long, it will have more time to apply force onto a ruler, so that will make it easier to fall.
Okay, but if the contact time is short and then the force will be small, and when the force is small, it won't be able to lift the paper upward, so that won't cause the force won't be able to lift the paper and cause a pressure difference under the paper. So I think if the ball is extremely elastic, it'll be more likely to fall.
Yes, but I think in your explanation, I think the most important part is still the ball's mass and how high it's dropped. So even though if it's contact in a very short time, if it's dropped by very very high height and very heavy, it will still fall even if it's contact a little bit.
Okay, so okay, and then move on to the next edge cases. Do you think what will happen if the ruler is extremely elastic or extremely close to a rigid body?
I have done a calculation in my theory and also done an experiment. And closer to a rigid body, it will support it more.
Support more means it will
be harder to fall.
harder to fall. Oh, okay. Okay, so I agree with your opinion. So I agree with your statement. So I think when the ruler is extremely close to a rigid body, it is easier to lift the paper up and the velocity that the paper moves up will be faster, so the pressure difference under the paper will be larger to push the ruler back down.
Yes, but I agree with you, but I think the most important part is still air pressure. The other is the main factor that is affecting this amount.
Okay, so and then what do you think will happen if the paper is extremely stiff or very soft?
Oh, if the paper is very stiff, it will be harder to form an air pocket. If it's very stiff, it will just flip it up and then all the air around it will just flow in and will just flip. But if it's very soft, it will form a little air pocket while other places goes down, and the pressure difference here will be big, and the air pressure will just.
Oh, but don't you think that when the paper is very stiff, it is hard to create it is hard to create an air pocket, right?
Yeah, so that means it's easier to flip.
Oh, okay, I agree with your statement. And so I want to discuss with you what is the definition of the ruler's fall again.
My fall is because in the problem statement it says flip. So sometimes when I do an experiment, it would just like if it's happened here, it sometimes just flip flop, just like flip flop.
You mean glide off?
Yes, that's.
And it keeps contact with the table until it.
Yeah, so I suppose in my definition that isn't flip. For my flip, I need to this ruler flips and also the paper flips with it.
So the paper also flips with it.
Yes.
So if the ruler moves up, will the paper slides backward toward the table?
No.
No, okay. Wait, okay, so, do you think the deformation of the ruler or the paper affects on your result of
Yeah.
the experiment?
Yes, I have done the deformation calculating by support coefficient right here, and the deformation of the paper will just affect how easy or not it will be able to form an air pocket, just like the stiff paper or the soft paper I just mentioned.
Okay. So. So let's go back to the edge cases. So, let me go back for a second. Okay, so you said that the friction doesn't really matter, but do you agree that there's still a little bit of deflection on your experiments?
Yeah, definitely, because
So-
it has contact.
I think if you want to fix this, if you want to consider the friction, I think you can add in the two forces that I said into your theoretical model, so that you can fix your theoretical model. Do you agree?
Yes, that will definitely affect, but I still think it's not a thing that will affect that much. So it's like considering the air viscosity. It's not an important factor.
Okay, can you turn to the page that the experimental setup that you use to fix the ball's position? Okay, so you said you use this to check if the ball falls on the same position on the ruler, right?
Yes.
Can you switch to any two of your experimental videos?
I didn't have an experiment video in this.
Okay. So can you search for any video that has the video of the balls hitting the ruler?
Okay.
So
Here.
So for this video, it seems that it hits a little bit close to the table. And can you change to the another video? So for this one, it seems to hit on the edge of the ruler, not close to the table. So what is the position, specific position that you hit the ruler?
That goes in with the torque. So here's the distance. Here's the distance between the ball contact point and the ruler, and here's the equation. So we can know how the torque is playing this phenomenon.
So you didn't fix the position, the specific position. So you use because you use this equation to calculate the torque, right?
Yes, so I could calculate the experiment because if I drop it like 3 centimeters away from the table, I just times that.
Okay, so what'll happen if the ball drops height? How do you fix the ball's drop height?
By just using the same ball dropping machine, like put it in the same place and do the experiment multiple times.
So you do not have to. Your ball drop height is always the same.
No, I mean, if I want to add, I will add some like books to add the height, so I can calculate how much centimeters from the ball dropper to the ruler.
Okay, and but every time, so this is a ruler,
Yes.
and so every time you drop the ball at different height maybe, and you sometimes drop here and sometimes you drop here as the so you don't fix the position.
No, that wouldn't happen because I would just here's the ball dropper here,
Yes.
and then I just add more things here to make it add more things here to make
Okay,
it.
time is up.
Thank you.
Paul, summarize discussion.
So we discussed the friction effect on the result of the experiment, and the report says the friction is actually negligible, but we think we should include it into the theory. And for the discussion of the edge cases for ruler, paper, and ball, when the ball is extremely elastic, the reporter says it will be less likely to flow. And for the position for the ball's contact point, and we also discussed the position of the ball's contact point and the shape of the ruler that considered in the theory. And We also discussed the definition of the ruler's fall. Okay. So that's all.
Okay. Questions from reviewer?
Can you turn to the graph that is related to air pressure?
Which I have a lot in the simulation, or
And what is the unit?
here, sine divided by cm.
Okay, another question is that you say that you use 5 papers together to do the experiment.
Yes.
And from 5 papers, you are actually changing the elasticity and thickness and weight at the same time, so you are changing multiple variables.
Yes, I understand your question, but so I have the explanation of if I put 5 layers of paper, that would be easier. It will be harder for it to form an air pocket. So that's my explanation.
What is your perspective?
Sorry, can you repeat the question again?
I say that what experiment is that the reporter places 5 papers at the same time, and this is changing the elasticity, weight, and thicknesses.
Yes, I agree with the review's viewpoint. Yes, and that's my answer.
And when you are doing the experiment, is 5 paper like will they separate?
No, it would just because it's new, so it's all the same. It's all very new and flat, so it would just be very together.
And another question is, in your 3D flow model, you say that like the paper and the table is parallel, right?
Yes.
But that is actually, I think it is different from your air pocket because it is parallel, but I don't think it is.
Yes. So the air because if I use the real model to put it in the Flow 3D, it will be a too complicating thing for the
So what is
software.
the difference between it?
There's not difference. The similarity is if it goes so fast, it will form a big pressure difference. It has very lot of similarities.
The theory is fit your result.
Yes.
Okay, so what is your point of view?
I think I agree with the reporter. So if we consider the if the ruler and the table is parallel, it will be too complicated for the calculation.
Okay, and the next question is about friction. When you are dropping the ball at different heights, it's actually changed the normal force. And normal force is in proportional to friction. So I think friction is actually a very important part in your experiment.
When the ball made contact ruler, that friction.
The friction between ruler and table.
Okay.
And when you are like dropping the ball from very high position, it's saying that the normal force become bigger, and then your friction will become bigger. Yeah. What's your?
I don't really understand your question because for my model it's like a seesaw, so they only make contact at this point. So the I don't see what's the frictions.
So the ruler won't slide during the
Okay,
experiment.
time is up. Will reviewer prepare for 2 minutes? reviewer takes the floor.
Okay, so I'm a reviewer from Los Angeles, and I'm going to make a review. So, report summary is that it have the reporter make a lot of models and have like 3D flows and using like the theory of air pockets and have many theories and also different layers of paper and do a lot of experiments. So I think we do good experiment, but but he didn't consider many things. Like what I just say is like if you have so many layers of paper, you are actually changing multiple variables, and you are not connecting your theory with your result. And actually, I think your data, you are actually a little lack of data. So which make your experiment much remains to be done. And about the opponent, I think she talked too much about the theory and ignore the experimental results. So I think opponent is not discussing the result a lot. And actually, I think the results, the data have a lot of problems. And the first question is, the opponent asks, does materials make difference on the phenomenon? And the reporter answers, yes. The next question is, the opponent asks how to define the fall of the ruler. And the reporter said, has to be both the paper and the ruler fall. So he said that because of this, so friction is not the important thing to consider about. But in my perspective, it is not good enough, and you are not considering all the things. The next question is, opponent asks, did you consider friction of different platforms? Reporter said, reporter said no, but it will only have a small difference, so they are not changing a lot. But I think friction is very important because what I just say is, the friction maybe it is different that if your friction is big enough, it makes your ruler split. But if your friction is small, it makes your ruler slide. But both of them is like making the ruler fall. So I think it is important. And the next question is, opponent asked about the elastic or rigid ball. And reporter response is, depends on contact time, mass, and height are more important variables. And then opponent asked about stiff paper. And reporter response is, stiff paper is easy to flip. Soft paper more easy to create air pockets. And then she asked, will the paper slide backward? Reporter say no. The next one is about the deformation of the ruler and paper. And reporter say, consider in theory. And then she asked about the experiment setup. And the reporter have no videos about the observation. Okay, that is
Okay, time's up. Reporter making the concluding remark.
Hi, I'm a reporter. I'm here to do my concluding remarks. So here's a problem statement. So I have to explain this phenomenon, investigate the regular parameters about the ball and the ruler. And then in my theory, I use this air pressure and aerodynamic to explain why would it changes the result that much. And then I use the torque to analyze all the objects. And I finally use flow 3D for my simulation to prove my point. And then in parameters, I have these 5 different parameters. And in my setup, I have a dropper to drop the ball. So the points in the discussion is talked about. So the definition of flipping the ruler. So if the definition is according to opponents and the reviewers, if it's sliding down, it will have some amount of friction. But in my theory, I want everything to flip, so that friction will be very small in this model. and the material, different material will change the parameters of the ball, and then I said it will affect the contact time, which will affect the force applied onto the ruler. And it also asked about lastly of the ball. It's the same answer as the last one. And then yes, and you asked me about the soft or hard paper to use. And my answer is, if it's a harder paper, the air pocket will not be easily formed, while the softer one would just bend easily. And then the reporter asked me if it dropped in the same place, and then I used the same dropper, so it will always be the same place, and I've considered the drop point in my torque calculation in my theory. And then he asked me if the Flow 3D is not accurate to a model, and it will be too complicated if I actually use the real life model inside, so it's simplified that way, so I could show what the air pressure would change on different angular velocity of the ruler. And then also asked me about the deformation of the paper. It will changes how the air pockets form and the air pocket size. And if the size bigger, the area of force from air pressure is bigger. And thank you, that's my remark.
Okay, and questions from the jury?
Yeah, a question for you, Laura. You did some experiment on the elasticity of the rulers and came up with number for metal, plastic, and wood.
Yes.
Did you use that number for the meta analysis?
Yes.
Which part I didn't show? Because
Okay.
you conclude that the elasticity is more elastic, is easy to fit, right?
Yes, it's in the torque law expression like here. The alpha here is the value I calculated here.
Well, I was asking experiment.
What?
Experiment. Did you do any experiment to show this?
In my experiment, the orange line here is drew by using the torque analyzed. But the reason for the torque analyzed and my results are so big different is because the air pressure is pressing from. So the orange line here is considering with no air pressure in a vacuum.
But this one is for given ruler,
Oh,
right?
okay.
So what if you use different ruler, how is it going to be?
Yes, it's here. So if the support coefficient is bigger, it will have more. It can hold more torque.
How the elasticity related to this supporting coefficient?
Supporting coefficient is calculated in my very first theory. It's about I use a force sensor and to pull the ruler to know how much deformation it can hold when force is applied.
So the higher number of this supporting coefficient is more rigid,
Yes.
but the highest torque is higher, right?
Yes.
Why the friction is important or isn't important?
So, okay. In my model, it's considered as like a seesaw motion. So if it's flipping, it's only the contact point is here. So the friction is very little to none.
So,
Okay, so so if the ruler plays like this and the paper plays like this, and when the ruler lifts up the paper will create an air pocket like this, right? So the platform over here is, so when the paper creates an air pocket, you have to discuss the friction that the ruler and between the ruler and the platform, because the paper moves like this when it creates an air pocket.
I think what the reporter just said is theoretically possible, but it is not like actually in real life, because I also do this experiment and every time I found that the ruler is also sliding and rotating at the same time. So I think friction is very important.
So I would like to ask maybe first the opponent and then reviewer and then finally reporter about the definition of y-axis in this data or any data the reporter show. Yeah, maybe start from the opponent. What is the definition of the y-axis in this data?
What is the highest torque of the pressure difference?
If you finish then.
I think it is the highest torque that the setup can support. So we make the graph. So this is like the force and the product of force and the weight. So this is my perspective.
The opponent is correct. I mean the reverse is correct because it's the flip point of my experiment. So I test all the height until it flips, and then the height before it flips is the highest torque it can hold. Highest torque before flipping, like what I mean.
Can you go to your page 93? Yeah, in this simulation, the red curve always has been noisy signal at the beginning. What does that mean?
Oh, it's like kind of like this, and the reason for this is the air cavity resonance. So if you move the air molecules, it will sometimes collide with each other and then have some viscosity. So that would not be a perfect line like here. But after a little time of oscillating, it will go back to the same and then create a big air pressure difference later.
So does that cause any displacement for your ruler or?
No, because it's just like how the air molecule is starting to move.
Okay. Do you have any opinion about this?
My opinion is, I think the noise is too big. Yeah, like after you can see the right part of the graph. I mean the level and the beginning is like it's just not a lot of difference. So I think the noise is too big.
I think, as you can see, the pressure eventually falls. So I think the reporter should explain why this happens.
Yeah. Okay, thank you. Receive it. Okay, for a reporter. $99977. For the opponent, 88865. For the reviewer, 66665.